Next we will be taking some examples of syntax directed translation. So, we will be taking an exercise which will be like this. So, we want to we know the grammar for regular expressions. So, from the regular expression we need to convert to NFA. So, can we have a compiler assisted technique for doing that? So, the job is to convert a regular expression to NFA. Okay. So, this if we can do, so we can have an automated tool for that purpose. Of course, in our lexical analysis chapter we have seen the things to be done. So, you can formalize it and put it into one compiler construction step, so that you can do this, we can have this conversion part automated. So, for the regular expression, the grammar that we consider is like this: R producing R or R, then R producing R R, then R producing R star, and also we have got the terminal symbols like say A. So, R producing A and it can give me epsilon. So, these are the rules that we have for the regular expression. Now, for syntax directed translation, so what we will assume is that we have got some attributes. So, each regular expression, for that we have a corresponding NFA, and the NFA has got a start state and a number of final states. So, that these are there. So, if we assume that for every regular expression, so we will maintain its corresponding NFA as an attribute of it, then we can combine those attributes as say syntax directed translation actions, and so that I can get the NFA for the complete expression, for the complete regular expression. So, let us take the first rule like say R producing R1 or R2. So, I am purposefully writing it as R1 and R2, so that in my action part, so I can very clearly mean like which attribute, whose attribute I am talking about. Okay. So, otherwise they are all regular expressions R, R1, R2, so they are all regular expressions. So, on the right hand side I have got two regular expressions, they are concatenated by they are connected by the OR operator, and then that gives me the overall regular expression. So, and for the rule for this, if I have got a regular expression for R1 and there is a regular expression for R2, so it has got a start state and a final state. So, it has got a start state and a final state. So, this is for R1 and this is for R2. Now, if you look into this construction example, then it says that you have to have a new state and add some epsilon transitions to them. Okay. And then you should have another new state which will be called the final node, then you will be adding epsilon transitions from here. So, this is the action to be done. Okay. So, how are you going to write? So, we write it like this. So, P is a pointer which is get new node. We assume that we have a function get new node. So, if you call this function, it will return you a new node of the graph. Okay. So, this is so we will call that function. Then I have to, so this is I have got this new node now. I have to add this epsilon transitions. So, I do add transition, what transition? So, a transition when I say, so I have to tell the start state, I have to tell the final state, and I have to tell what is the label. So, these are the three things to be said. Okay. So, start state is this new state that I have taken, then this destination state is this state I am talking about. So, this R1's start node. So, if I assume that there is a function called start node, so such that if you pass the graph of R1 to it, so it will return its start node. So, this is start node of R1 dot graph, and I have to tell what is the label. So, label is epsilon. So, I assume that there is a function called add transition. So, if you call this function, so it will add transition between node 1 to node 2. So, node 1 is P in our case, node 2 is the start node of R1, and then the transition that is added is labeled with epsilon. So, that is add transition. Then I can, so this is done. Now, for the second one I have to do another transition has to be added for R2. So, for that I can do add transition P start node of R2 dot graph and label is epsilon, that add transition can be done. Now, so this part I have made. So, once I have this R1 and R2 these graphs available, so I have made this left part of the diagram. Now, for the right side, for the right side what I have to do is, so I have to get another node. So, I say q equal to get new node and that will be a terminal node. So, we will come to come later how to make it a terminal node. So, that we will do later. Now, this node this graph R1 may have several final states, and for each of these final states I have to add this epsilon transitions. So, I write like this, that for each n in final nodes of, so I assume again that there is a function called final nodes that returns the set of final nodes of a graph. So, R1 dot graph. Okay. So, for each node n in final nodes of R1 dot graph, do we add transition from this final this n to q with label as epsilon, fine. And similarly, for R2 also I need to do the same thing, that for each n in final nodes of R2 dot graph do add transition n q epsilon. So, once we have done that, so these transitions have been added. Now, what we have not done so far is marking this node as the start node and marking this node as the final node. So, marking P as the start node and marking Q as the final node of the graph. So, we assume that there is a function called mark final which will mark the q node q as a final node, and then we say that we have to mark P as a start node. So, I say that as if I have got another function that mark start P. So, this is made the start node of P, and then the attribute R dot graph is made equal to P. So, this way I can write the syntax directed translation scheme, so that for R1 or R2 I can get the corresponding NFA by combining the NFAs of R1 and R2. So, next we will be looking into the NFA for this R1 R2. So, the second rule. So, R producing concatenation R1 R2. So, here, so we can say that the rules that will, the code that we will have, or the actions that we have is that, so here I have to add transitions, like if this is R1 and this is R2, then what we do is from the final state of R1, from all final states of R1, so we add epsilon transitions to this initial state of R2. So, that is the action. So, we write it like this, that for each n in final states, final nodes of R1 dot graph, final nodes of R1 dot graph do. So, what do we do? We add transition So, add transition n from n to the start node of R2 dot graph, start node of R2 dot graph, and the label being epsilon. So, this is the transition that we have added, and then we have to say that as now R dot graph can be simply made equal to R1 dot graph. Okay. And then I have to mark the final states. So, mark final for this particular graph R. So, I have to the final states of R will be the final states of R2. So, this is mark final. So, from the by applying the function final nodes, I get the final nodes of R2. So, that is R1 R2. So, this way we can do it for this R concatenation of two states. Now, I need to do it for R star. So, how do we do it for R star? So, R producing R star, and this is a bit tricky, because you know that what we need to do is, if this is the situation, then I have to have one epsilon transition from here to here, I have to have an epsilon transition from here to here, I should have an epsilon transition like this, and I should have an epsilon transition like this. So, these are the things to be done for converting R to from R to get the NFA for R star. Okay. So, what we do? We do it like this. So, I have to add this epsilon transition. So, first we do the epsilon transition addition from the final states of R to its initial state. So, that part we do, we write it like this: for each n in final nodes of R1 dot graph. Okay. So, what do we do? We add the epsilon transitions. So, that is add transition in start node of R1 and the label is epsilon. So, these transitions have been added. So, these transitions are now done. Okay. Next, I have to add this start state. So, for that I have to get a new node. So, P as get new node, okay. And then this is the start node of P of the graph G. So, mark P as start node of R dot graph. Now, I have to add the epsilon transition from this node P to the start node of R1. So, we say add transition P comma start node of R1 dot graph and the label being epsilon. So, that this transition has been added now. Now, I have to add this transition. So, for that I have to get another node. So, that is called Q. So, that is another get new node. So, after I have got the node, so I do an add transition P Q epsilon. So, this transition is added from P to Q, epsilon, label being epsilon. Now, I have to add this transition. So, for every final state that I have here in R 1, so these epsilon transitions are to be added. So, I do it like this for each n in final nodes of R 1 dot graph do at transition n q epsilon. Okay. So, these epsilon transitions have been added, and then I have to mark this q as the final state. So, mark final q, and then we have to say that this r dot graph equal to p. Okay. So, this way we can write down the syntax directed translation scheme for the converting this regular expression R to R star. Now, there are two more simple rules that I have got. So, R producing A. So, for R producing A, so what I have to do is I have to have something like this, and this is A. So, this was the thing. So, how to do this? So, I write like P equal to get new node. So, I have to first of all create two nodes, one for one will act as the start node, other will act as the end node, the terminal node, and Q. So, they are the two nodes that I have got, P and Q, and then I have to add transition from P to Q, add transition from P to Q, and the label of the transition is A. Okay. Then I have to say that Q is a final state. So, that can be done by calling the function mark final. Okay. Then to mark P as the start node. So, that is by calling the function say mark start P, and then I have to say that R dot graph equal to P. So, this is for R producing A. So, only the single terminal symbol, and what remains is the epsilon transition R producing epsilon. So, R producing epsilon. So, here also it is similar, only thing is that this label is epsilon. So, the code for this is same as this one, but only instead of A we will be adding the epsilon. So, we will have like P equal to get new node, Q equal to get new node. So, everything will be same, only in the add transition part. So, this should be P Q and the label is epsilon. So, rest of the thing will be as it is. Okay. So, if you have this set of rules, then so by syntax directed translation mechanism, so you can easily generate the corresponding NFA from some regular expression. So, next we will be using another example for this syntax directed translation, which is for evaluating the arithmetic expressions. Suppose we have got the arithmetic expression grammar, which is given by this. So, E producing E plus E or E minus E or E star E, then E division E within bracket E, and then unary minus we write it as a separate token, separate terminal symbol u minus. So that to differentiate it from the binary minus, and it can be a simple number. Suppose this is the grammar that is given. So, we know how to generate the corresponding parser. So, that we have already learned. Now, for syntax directed translation, like we want to evaluate an expression. So, how to do this? So, we assume that with this with the non terminal e, so we have got an attribute which is e dot val. So, which will hold the value of the expression. So, if the value of the expression, if it is a, so since this is a number, so you note that this is not an ID, so this is a number. So, at the compilation stage itself, we will be able to compute the value of the expression. So, it does not need to go to the runtime thing. So, that is why, so it is useful, like maybe while writing some expression, we have written like 2 into 3 plus 5. So, for the programmer's ease, so it is written like this, but the compiler can easily convert it into the number, that is 11. So, how that conversion from this, so this is coming in the source text and how it is getting converted to 11. So, that you can do by means of this syntax directed translation mechanism, and we assume that we have got an attribute val, so which will be holding the value of the expression. So, you can very easily guess like what can be the syntax directed translation schemes for this thing, like say E producing E1 or E2. Okay. So, in this case the action is nothing but, so I have to compute this E dot val equal to E1 dot val plus E2 dot val. So, this simply may be the action. So, because those two values are to be added, so E1 dot val, that attribute contains the value of the expression E1, and E2 dot val contains the value of the expression E2. So, I can just add them by making this E1 dot val plus E2 dot val. Similarly, this E1 minus E2, so E producing E1 minus E2. So, there also you can write the syntax directed translation scheme like E dot val equal to E1 dot val minus E2 dot val, fine. Then E producing say E1 star E2, E1 star E2. So, there also you can write like E dot val is E1 dot val multiplied by E2 dot val. Then E slash E division, E slash E. So, this E dot val equal to E1 dot val divided by E2 dot val. Then unary minus E1. So, this I can say that E dot val equal to minus of E1 dot val, and E producing number. So, within bracket E producing within bracket E1. So, this is very simple, that E dot val is nothing but E1 dot val, and then I should have this E producing number. So, here this E dot val will be equal to, the lexical analyzer is if we assume that it has returned the value of this token number onto the into one attribute of it, which is num dot val. So, this will be equal to num dot val. Okay. So, you can check like how it will work, like if I have got an expression like say 2 plus 3 into 5 slash 9. So, if we have got something like this, then say plus minus 5. Okay. So, how will it look like? The expression, the parse tree will be like this. So, this is E plus E, this E gives me within bracket E, this E gives me unary minus, then E, then this E gives me number which is equal to 5. Then this part will be giving me E slash E, okay, and this slash E. So, this E gives me a number whose value is 9. Now, this E will be giving me within bracket E like that, and that will give me E star E. Now, this E will give me a number which is equal to 5. Now, this E will give me within bracket E. So, that will give me E plus E. So, that will give me number, that is 2. This will give me number, that is 3. So, this is the parse tree that will be produced by the parser. Now, this syntax directed translation rules, so they are applied when we are doing the reductions. So, when the shift reduce parser, so it will do the reduction. So, it will first do this reduction. So, this as a result the corresponding val attribute will be equal to 2 by this rule. So, this E dot val equal to num dot val. So, this val equal to 2. So, this val will become equal to 3. Now, this will be doing the addition E1 dot val plus E2 dot val. So, this value will become equal to 5, fine. Now, this is within bracket E. So, this will also become equal to 5. Now, this will make it 5. So, now this is 5 into 5. So, this will make it, this value will be made equal to 25. So, this will also be made equal to 25, because E within bracket E is E dot val equal to E1 dot val by this rule. So, this is also 25. Now, this when this reduction is done, so this E dot val will be equal to 9. Now, when this reduction will happen, so 25 by 9. So, if I assume it is an integer division, so this will give me 2. So, this is E dot val attribute will be equal to 2. Now, this side, so this E dot val equal to number dot val, that is 5, then this unary minus, so this will become minus 5. So, this will give us minus 5, and finally, this E dot val, so it is 2 plus minus 5, that is equal to minus 3. So, it will get that E dot val computed as minus 3. So, in this way you see at the syntax directed translation mechanism. So, we can write down a set of actions, so that if those actions are taken during the parse tree reduction process, so it will be able to compute, it will be able to do many useful computations. So, in this particular example, so it is doing, it is finding the value of integer expressions, and previously we have seen a technique by which we can convert this regular expression to NFA. So, that conversion, so we can have appropriate functions written, so that I can easily get the corresponding graphs. So, this way the syntax directed translation can be useful for in the parsing process, in integrated fashion with the parsing process, so that you can do many useful jobs done by the parser itself.